So the probability of successive events builds off of the fundamental counting principle, which just says multiply the probability of each event happening, even if they're conditional probabilities. Let's read example 3 now. Example 3 says find the probability of successive events. A box contains 4 red, 3 white, and 5 green balls. Suppose that 3 balls are randomly selected from the box in succession without replacement. That means when they pull the ball, they do not put the ball back. It is absolutely key that you read that without replacement. When they pull the ball, they do not put the ball back. So that means we're going to have to recalculate our probability every single time. So it says, what is the probability that the first ball is red, then you have a white, and then you have a green? Okay. So the bottom is always, what's the total set that I'm considering? Well, if I do 4 plus 3 plus 5, which is the 4 reds, the 3 whites, and the 5 greens, seems to me that I'd have 12 total balls when I start. Okay, so if I wanted to find, I haven't drawn any balls yet, I have 12 balls in the bag, and I want to pick that first bag, and I want it to be red. There are 4 reds out of the 12 total balls. Okay, so we did not put that ball back. Let's think about what's left in that bag. Well, since I took out 1 red ball, there are not 12 balls anymore. There's only 11 balls left in the bag. And 1 of the red balls is gone. There's still 3 white balls to pick from. So now my probability of getting a white on the second ball would be 3/11. Now I've pulled a white ball out of there. There was 12 balls. I pulled the red. There was 11. I pulled the white. So now there would be 10 balls left in the bag. I've pulled a red and a white. So all the green balls are there. So there's still 5 green balls left. So go ahead and put this into your calculator. Again, we're going to multiply each one of these probabilities. We're going to simplify it in our calculator. Our calculator does it for us. I'm getting a fraction of 1/22, or 1 over 22. So let's try this again. Let's try part B. It says, what is the probability that 2 white balls followed by a green ball are selected? So let's think about each of our things. We have a white, and then a green. So again, we're going to start off with 12 balls. After we pick a ball, we'd have 11 balls, and then we'd have 10 balls. So the denominator is not too bad. It's going to decrease by 1 every single time because I pick 1 ball each spot. So the first one wanted to be a white ball. When I picked a white ball, there were 3 white balls to pick from. Now that I've picked 1 of the white balls out, there's only 11 balls left, and further, there's no longer 3 white balls left. There's only 2 white balls left. I go on to my third ball, the green ball. There's only 10 balls left in the bag, but all of the greens are there, so that would be 5/10. Go ahead and put 3/12 times 2/11 times 5/10 in your calculator and simplify. I'm getting 1/44. Let's try example 4. It says a standard deck of playing cards is shuffled and 3 cards are dealt. So if it's dealt, that means there's no replacement. So you're not putting that card back in. So the first card, now there's only 51 cards left, then there's 50 cards left, etc. So it says find the probability that the cards dealt are spade followed by a heart followed by a spade. So spade, then a heart, then a spade. So we have 3 cards that we want. We're going to multiply these probabilities. I want a spade, a heart, and then a spade. So let's think about it. I start off by having 52 cards. How many spades do I have? Well, there's 13 cards in each suit, so that'd be 13 over 52. After I've been dealt that card, how many cards are left in the deck? There's only 51 cards left in the deck. How many hearts are left? All 13 hearts are still left in that deck. Now I've been dealt 2 cards, so I'm down to 50 cards in the deck. And now I need to consider how many spades are left. Well, I already picked off 1 of the 13 spades, so there's only 12 spades left at this point in time. So go ahead and do 13 over 52 times 13 over 51 times 12 over 50 into your calculator, and let's see what you get as a simplified fraction, because this did not ask for a decimal. I'm getting 13 over 850 is the probability. All right. Let's move on to independent events. It says earlier in this section, we considered the probability of drawing 2 aces in a row from a standard deck of playing cards. Because the cards were drawn without replacement, the probability of the ace on the second draw depended on the probability of the first draw. So what we did was we said that first ace was 4 out of 52, and then we said the second ace, because that card was not put back, there was only 3 aces left in 51. So now, what if that card was picked back is what we're looking at. So what if there was replacement? Well, think about that second ace. That second ace, there would no longer be 51 cards left. There would still be 52 cards left. And what about the number of aces? Well, there would still be 4 aces left. So if I want to draw an ace and then an ace with replacement, I would have 4 over 52 times 4 over 52. So this is called an independent event, where the second event, drawing the second ace, did not depend on what happened on the first one. So the key to this one is with replacement. If you allow replacement, you do it just as we've done the entire sections, all the sections so far, is you're just going to look at each individual event and take the probabilities of each individual event, regardless of what happened prior to it, and multiply them together. That's what it says here for the product rule of independent events. It says if they have nothing to do with each other, just multiply their probabilities. We've seen this before. So let's read this paragraph just to make sure we get through it. It says, now consider the case of tossing a coin twice. The outcome of the first toss has no effect on the outcome of the second toss. So the probability of the coin flipping head or tail on the second toss is not affected by the result of first toss. When this comes to the event, outcome of the first event does not affect the outcome of the second event. These are called independent. Okay, so let's consider a problem that we did many times before. It was find the probability of getting heads, heads, heads. And when we did this, we looked at the total of 8 possibilities. So it could have been heads, heads, heads. Could have been heads, heads, tails. Could have been heads, tails, heads. Could have been tails, heads, heads. Could have been, what else could we have here? We could have heads, tails, tails. We could have tails, heads, tails, tails, heads, heads, and tails, tails, tails. Or sorry, tails, tails, heads was the last one. Tails, tails, heads. And then we could have had tails, tails, tails. So those are the 8, and we got those by looking at the tree of each of the choices. And so we said the probability of getting heads, heads, heads was 1 out of 8. Well, what this is giving us is telling us that flipping a coin each one of these times is an independent event. Each one of these have nothing to do with the other. So what would you do? You would look at what's the probability of getting heads on the first one, the probability of getting heads on the second one, and the probability of getting heads on the third one. Because they're independent, we don't care about what happened on the previous one. So the probability of getting heads is 1/2. Heads is 1/2, heads is 1/2, which gives us our total probability of 1/8. So if we use this new product rule for independent events, the probability of getting heads, 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 we don't need to look at all 8 possible outcomes. All we have to do is consider each individual coin flip and multiply those probabilities. It doesn't let us see the sample space to what it is, but it does help us get the answer to the individual question, what's the probability of getting heads, 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 significantly faster.